Am I still audible?
Yes, yes, Johnny. Please continue.
Yes, sir. Yes, sir.
Okay. This week had a lot of formulae and all, but I did not compile this that you can screenshot. But these will be used again next week. So this week we started with these performance metrics of a link that we have designed. So we'll generally be concerned with the bit error rate. So for optical communications, we need usually 10⁻⁻⁹ as a bit error rate. So, or you can even go higher. But optical communications basically form the backbone of the communication system. For example, this is mobile phone cell towers talk to each other using optical communication. Right? So here we need a low bit error rate. Then we introduce these concepts like quality factor and how we make decisions whether we have detected 1 bit or a 0 bit. That will be decided using some decision threshold for the current we have detected, and how the noise will affect the detected signal and how we can encounter errors. And quality factor was defined using this current and threshold values and the variance of the noise. Then again we introduced this concept of receiver sensitivity, which is the minimum power required for some amount of behavior, and we related the two quantities. And then finally we also introduced the concept of signal to noise ratio. The formulas are for linear scale, so be comfortable with this changing from logarithmic and linear. Most of the formulas introduced this week are linear. By default is linear. If it is same then this logarithmic. For example, whenever you're dividing something or multiplying something, log scale is more comfortable. Yes. And initially we discussed for thermal noise limited system, which is the typical OOK system performance. And then we also discussed this quantum limit of photo detection that was regarding a short noise limited system. Either you can have high number of photons, that could be one case, or very low thermal noise, which is basically a frozen system like quantum computing and all these things, quantum key distribution. Those will use this regime. So the formulas will be different. Then we went ahead and introduced these optical amplifiers and why electrical amplifiers is a bad idea. And this one-hour regeneration is possible using this EDFA. We also talked about this silicon optical amplifier and just mentioned Raman amplifier. Silicon optical amplifier is basically the repetition of the laser concept without the cavity. That's it. So there is no feedback, but it is spontaneous emission that is achieving the amplification. And before going to EDFA, we also introduced all these things that are desirable. What is the goal of the optical amplifier? We want high gain, high bandwidth, and the gain we want as flat. Then noise figure we want low, which is noise figure is just output SNR by input SNR. And because most of the communication systems will use polarization multiplex signal, we also want polarization independent amplifier. Then if we are using multiple channels, we want minimum crosstalk. And then For amplification, we will have to give some pump power. So we want the pump power to be converted to this signal power as efficiently as possible. All these metrics we need. And commercially, FPAs are the most popular. They serve this, most of the communication needs for now. For ultra wideband applications, this is an active field of research. So research is still going on. This silicon optical amplifier and also some optical amplifiers using nonlinear effects. Those are still going. So basically, this FA works under the principle of simulated emission, just like we discussed in lasers. But in lasers, we achieve population inversion using an electrical pump. So we pass current through the medium, and the electron hole pairs will generate. And here we will pump the medium using optical means. So some 980 nanometer pump will be used for that pump, and it will transmit in at C band. Our signal at C band will be amplified, and then discussed in a few videos about this gain per unit length. They repeated some concepts from laser. Then how the gain spectrum is this absorption and emission spectra, how they look like, which are not flat. That was shown. And then how the gain spectrum was flattened, how we use some additional filters to flatten the gain. That was shown. Then we briefly touched upon this signal saturation, how the FR cannot amplify indefinitely. Like it is limited by the population inversion. So if your signal power is too high, you will see a lower gain. So some curves were shown in the video. And then the concept most relevant to our link design problem. We want to move towards the OSNR, how much the optical SNR degrades each time you introduce an amplifier. So that is mostly due to amplified spontaneous emission, because just like your signals can cause stimulated emission, if there is population inversion, there will also be some spontaneous emission like LEDs. So that will also cause some noise. So in the case of laser, this was the main, this was the beginning point of any laser, and we will put it inside a cavity so that it gets amplified. Amplified indefinitely, like some selected modes will be amplified indefinitely. Here there is no cavity, but the operation principle is similar. Like it still operates under simulated emission. That much. And then we saw the what is the in-band noise that we will see at the receiver. When we are talking about SNR, we are moving back to this electrical domain. So we'll see what is the in-band noise, computer signal, ASP beat noise. The last two videos of this week were heavy with these formulas and stuff. So we'll go through those. And here we ended with this noise figure and how SNR degrades, what is the minimum limit of SNR degradation. So no ETFA can work, no ETFA can have noise figure below 3 dB. You will need to use some other means if you want to go below. And typical ETFA noise figures will be 4-5 dB. That's where this week ended. And next week we will start proper link design. That's all that was covered this week. Formulas I did not compile. Sorry about that.
Jone, can you any MATLAB code for to calculate bit error and quality factor error?
This week I don't have.
Okay, this week you have not. So, can you ask your doubt regarding this? Anyone have any doubt regarding previous session or this? Unmute yourself and you can ask your doubt. First we have discussed about your doubt and then we have to discuss. Jagannath, Gauri, Somil, Akansa, Anim, and if anyone have any doubt you can ask to that.
Sir, can I ask the assignment question?
Yes, yes.
I have, sir, question number 4 and 5.
For assignment,
Yes.
question number 4 and 5. Hello?
Find the receiver sensitivity for VR. VR is given.
So you have to calculate that short noise formula. From that you can that maybe I have that formula.
Yeah, receiver sensitivity there was
Yes, yes. It is quality factor under risk of that variance upon that responsivity.
yeah, and assume thermal noise limited system.
Yes.
That's all. Soft noise, thermal noise, and cold noise.
And next is that find the receiver sensitivity if the bit error is limited by the thermal noise. One is for the short noise and another one in one case the sigma t equal to 0. Jagannath?
Okay, I'll stop this.
Yes, sir.
So in that formula is a q root square of that sigma t square upon rd, and in one case you have to assume that sigma t equal to 0 in that case for that thermal noise or that. It is just formula based that.
Okay, sir.
Okay. Anything others? I think that Akansa, Kalyani, Meenakshi, are you there?
Yes, sir.
Have you any doubt, Kalyani?
No, sir.
Don't agitate. Whatever that you have doubt, you can ask to us that. It's not about that class. It's about the course or whatever that you have doubt it regarding optical fiber and that.
Sir,
Yes.
sir, due to some work in our college, I not able to watch this week video properly. So, can you give a short preview about this, sir?
For what?
There should be a folder. To the right side, there are weeks listed, right?
Yes, sir.
In the course page, towards the bottom, there is a link, I think, called. Wait, let me check. This text transcripts.
Yeah, yes, sir. Yes, sir. That's why I go through that.
But like it's not divided into weeks, I think.
Yes, sir. If
So
I
it
click,
has
lead to some Google Drive. the Google Drive, I think it's based from the right from lecture number 1. It's there, so that's why I'm searching, sir.
Okay, I don't know the exact numbers, but you can find continuously the notes for this. I think it starts at lecture 69 this week.
Yes, today is from 69. That week 8 is start from 69.
So
Okay.
you might go through those for this. But like I think going through the videos will be the quickest way. Just watch it at increased speed, no? Like instead of watching it at 1x speed, it's a YouTube player, just watch it at 1.25 or something. It's 3 hours of lectures, I think.
Yes, sir. Okay, sir.
So, I don't know. I mean, in my opinion, that's still the best way to revise.
Sumil, Akansa, Gori. Any doubt?
Sir, last time week assignment solutions not uploaded, sir.
Okay, I'll tell the NPTEL team. Sometimes they forget, but solutions are already in the website. They're still in private, so they will be released as soon as possible.
So today we have to discuss about that as per the Zonex said that performance parameter for the link design and uh, fiber link design. So we use that in this case is non-return to zero OK modulation scheme in this discussion. So what is the performance parameter of that link? We have to calculate that what parameter will affect that performance of that link through which we have to communicate the data through transmitter and receiver. So this lecture is on basis on that we have to calculate bit error rate, signal to noise ratio, quality factor, what are the effect of the thermal noise, short noise. Then we have to discuss about that amplifier, types of the amplifier, why we need the amplifier, what is the requirement of the amplifier. So we have discussed about these things. So if you have any doubt or I need all the participants should be speak and then yes Jagannath, you want to speak something?
Yes, sir. Sir, in question number 10, I have solved up to the formula is equal to G naught by 1 plus by B. Sir, how to be done?
Jagannath, your voice will be break, not proper audible. Can you pattern again?
Okay.
Hello?
Am I audible?
Yes, yes.
Finally, I get G is equal to G naught by 1.1. After that, sir, how can I find out the P out?
Your voice is still not audible. It is breaking between that. Either you write in the message chat box or we can read that your questions. Can you write in chat box? If some issue in the mic and some network issue. Jagannath?
Yes, sir. Yes, sir. Am I audible now?
Yes, yes, tell them.
Yes, yes.
This is
Sir, there is some network issue actually. Sir, in question number 10, assignment 8, let's
Yeah.
solve up to the formula that is G is equal to G naught by 1 plus B in by B saturate. Sir,
Yes.
I got G is equal to G naught by 1.1.
Okay.
Then, sir, how can I calculate the P out? P out and P saturate. P saturate I have. How to calculate the P out? What is the formula, sir?
Uh, so gain will be P out by P in linear scale. Just to,
Sir,
gain, what is
Gain,
gain?
this gain equal to P out by P in. The gain formula is P out by P in.
yes, sir.
So you have given the P in and G, and then from that you can calculate up to the P out.
Okay, sir.
Okay.
I have got.
So uh, we have to move. So what the quantification of the performance of the any optical link, like that we have the any optical link, we have there is a transmitter, some amplifier in between that, this is the detector, some is isolator, and that between in that connector will be between that. So how we quantifying the performance of the optical link, what are the performance parameter which is important for the design of the optical link? From that student, can anyone tell me that, some idea? Anyone can unmute yourself and can anything you know that whatever that. So first we have already joined that we have important is a bit error rate, and second important parameter is a receiver sensitivity. So bit error rate is what significance that it will be defined as that number of the incorrect bits upon number of the transmitted bits. Whatever the incorrect bits we have received and whatever the total number of the bits we have to transform. So for any good optical link design, we need that bit error rate should be less than 1 into 10 to the power 9 minus 9. We have to take care that our bit error rate of the optical link should be 1 into 10 to the power minus 9. So it will be give us the probability of incorrect identification of the bits. How much the bit will be lost in between that design through the amplifier or that isolator or that connector, through the transmitter or maybe through the receiver side that. So we have got that we can know through this bit error rate only that. So for any optical link design, we acceptable bit error rate should be 1 into 10 to the power minus 9, and whatever it implies that what is the meaning of that 1 into 10 to the power minus 9, that error should be less than the 1 bit for transmission of over 1 into 10 to the power minus 1 into 10 to the power. If we transmit 1 into 10 to the power plus 9 bits, so error should be less than equal to 1 bits. We have the error should we can lose 1 bits in transmission of the 1 into 10 to the power 9 bits. So it is acceptable if we receive or we have error of the 1 bit on the receiver side, then our performance of the optical link is very good. If this error should be large, then we have to identify that whatever the happen in that optical link, so we have get the maximum bit error rate. Second is the receiver sensitivity. So whatever this receiver sensitivity should be significance, or we can calculate the average power required at the receiver to operate at specific bit error rate. Whatever this receiver side, whatever our average power required, so we can operate at we have to manage this bit error rate. So it will identify that whatever the receiver sensitivity, that it will measure that bit error rate of even that 1 into 10 to the power minus 9. So to operate that receiver we require some power. So the reason for the error in the optical link is only the noise. It is either thermal noise, short noise, Gaussian noise, quantization noise, error, filter noise. There is a lot of the type of the noise in that communication. So mainly we have to consider that in the optical fiber link we have to calculate thermal noise and short noise. So suppose we have to think that if you have any doubt in this, you can unmute yourself and ask me that. In between you can stop me. Suppose our receiver sensitivity average power, suppose I link that 1 microwatt. I suppose that our receiver sensitivity average power should be 1 microwatt, and the corresponding bit error rate equal to 1 into 10 की power minus 9. Okay, then suppose suppose our receiver average power will be down. This average power will be reduced anyhow, some supply or some any reason that in optical fiber it will be reduced to, it will be lower than less than equal to 1 microwatt. Then what happen, we cannot detect this bit error rate. Even we cannot identify that bit error rate should be equal to 1 into 10 to the power minus 9, means it equal to 1 nano ampere like that. So we have to maintain that average power of that receiver should be around 1 microwatt, or whatever the average power required we can calculate through that receiver sensitivity only. So two important factor uh, for our is that one is bit error rate and another is the receiver sensitivity. So last class, so we have like that signal like that. Sorry, we have like signal like that. There is the current signal. There is a signal current, and there is like time scale on which the signal will be moved. And this is the 0 and that axis, 0 axis, that x and y axis, and our signal will be moved like that. Okay, so this power where the signal will start is I0, where the maximum current will be reached is the I1. Okay, and this is the that middle line of that our current, and this middle line that intermediate current ID, that maximum, that root 2 mean square, that maximum current ID by 2. So we need to calculate this, we need to get the variance of that. We have calculated the Gaussian variance, Gaussian noise. In that case we have to apply that exponential function of distribution of that Gaussian distribution, and we have to calculate sigma 1 and sigma 2 variance for that to calculate that noise. So we have to calculate standard variance, and through which we can calculate the bit error rate of that signal. So in case of our thermal noise regime, we have that sigma 0 equivalent to sigma 1. In case of the thermal noise, if we have to calculate the thermal noise limited, we have the condition that both that variance for that I0 current and that I1 current, that maximum and high should be equal to, both should be the equivalent, because our thermal noise is like that, it will cover the whole area. Thermal noise, it spectrum is like that blank, it will cover the whole spectrum. That Gaussian spectrum, it will cover that whole spectrum. That's why we have to keep that variance of that I0 equal to variance of the I1, because it covers the whole spectrum. If you see that spectrum of that thermal noise or white noise, it should be the same. So this is the bit error rate I already explained you. Next requirement is, what is the requirement of the good receiver, and define the quality factor. What is the requirement? A good receiver have the what requirement? Anyone can?
Bit VR should be less.
VR should be less. But other things? Any other things? VR should be less.
Less noise.
Less noise. Then
Noise figure.
okay.
Signal to noise should be less.
Okay. So I already explained that that good receivers should have a large difference between I0 and I0, that corresponding variance should be very low. We required a very low corresponding variance. That's why that it have the less noise, because variance should be less. That it means variance means root mean square error, or root mean square of the noise will be given by the variance. If it will be less, then our system performance will be high. It will be less when then where the current between that I1 and I0 will be identical. It should be have a large ratio of amplitude of that current. Second, quality factor is defined at difference between I1 and I0 and inversely proportional to the speeds. What is the meaning of that? Anyone can tell me that meaning of that quality factor?
Transferring of messages will be increased widely.
What happened?
Inversely proportional means transferring of messages will spread widely.
Okay. Anything else? Anyone want to add something?
Q is equal to 1 by omega CR.
Okay.
Omega L by R.
So, like that, our bit error rate should be, we can 1/4. We have ERV function, because we have to calculate that through that Gaussian, that 1 minus ID upon sigma 1 by root 2 plus ID minus I0 bata sigma 0 by root 2. Okay. So in this we have the quality factor. We have mentioned that I0 minus I1 difference upon sigma 0 plus sigma 1 is variance spreading. Like that we have the like that this pulse, and we have Gaussian pulse, we have E minus X upon root sigma, and sigma 1 we have to define like that. Some function we have in the communication, or you have to read in mathematics. So this spreading we have to inversely proportional to that spreading of that noise, or that standard deviation. We have to calculate the deviation of that pulse, and then we have to calculate standard deviation in mathematics, or in communication signal you have measured that any communication signal we have measured that whatever the deviation with respect to signal, center signal, that FC frequency, the deviation from that signal from maximum value of the signal we have to calculate. So it will be directly correlate with that bit error rate of the signal. So in case of the thermal noise, I already told you that sigma 0 equivalent to sigma 1. So it will be equal in that case. Then whatever error in the bit error rate in the case of the sigma, that is come into 1/2 area function of q by root 2, because q we have to q already I have explained that q equal to I1 minus I0 upon sigma 1 sigma 2. So here q is the measurable quantity, and using q we can estimate that bit error rate of any signal. This means that bit error rate can be estimated without counting over, but simply by another noise in the signal. So we cannot calculate or identify whatever the bits we have to transmitted, but we can calculate bit error rate whatever the amount of the noise present in the that signal. So we can calculate through that noise, we can calculate a bit error rate, and through which we can say that our signal we have transmitted like 1 into 10 to the power 9 bits, and we have received 1 into 10 to the power 8 bits or 1 into 2 into 10 to the power 8 bits or 5 8 or 7 bits, and this is the error we have received at the receiver side. Through that noise we can calculate the bit error rate. We cannot calculate one by one bits we have to receive, and whatever the transmitted, we have only the solution to calculate a bit error rate should be that we calculate the noise. So we have to calculate the signal amplitude of the noise. We have calculate every time to noise the standard deviation, that sigma minus sigma 2. So we calculate whatever the amount of the current before that supply of the noise and after a receiver side. So we have to take the difference, and through this we have to calculate bit error rate. So this formula I have already explained at you. Suppose, can anyone tell me the answer of that questions? You have to given lambda equal to 155 nanometer. Responsivity RD you have to given 1 ampere per watt. Thermal noise standard deviation sigma 0 equal to sigma 1 you have to given 100 nanoampere. Find the receiver sensitivity. Whatever the receiver sensitivity in case of the average sensitivity in case of that thermal noise. Anyone can? So V average equal to Q sigma T upon RD. Okay, so you have to given that formula. Now you have to given that Q. How you calculate that Q? Anyone know that how can calculate the Q? If you have not given Q, how you identify that whatever the value of the Q at this bit error rate? If our bit error rate is 10 to the power minus 9, then what is the value of the quality factor in that case? So one graph is given that between that bit error rate and that quality factor that give the relationship that bit error rate get. This type of the graph will be you have to see, and this is the value of the bit error rate, and this is the value of the quality factor you have to given. So if my quality bit error rate is 10 to the power minus 9 like that, then I have to take a straight line and then I have to meet this. And this is the quality 6. Yeah, 6, 7, 5, 4, 3. So on this will become all like that, this will become all like that, this will become all like that. So if my bit error rate will be less, then there will be less quality factor. If it will likely proportional to that quality factor. So from this graph you can calculate that quality factor in the exam or everywhere. So you have to know that you have to given this graph either in the questions, or you have to remember that how can we whatever the around the value of that quality factor. So in case of that bit error rate in 10 to the power minus 9, quality factor is equal to 6. If it is 10 to the power minus 12, it will be quality factor equal to 7. So from this graph you can calculate the quality factor. So you have to Q equal to 6, sigma T has given you 100 nanoampere square, and RD has to given into to that 1 ampere per watt. So you can calculate through this that receiver sensitivity in this case. Manju sir, good evening. So have you any questions? Manju sir, can you unmute yourself? I think you joined first time, right? So this graph I have already explained that through this we have to calculate the quality factor there. Explain the important performance parameter of short distance link and long hole link with amplifier. What is that short distance link and long distance link, and how can you identify that?
Sir,
And
for
what is
long distance links, it is important parameter is SNR.
SNR? So what is the SNR? What do you mean by the SNR?
Signal to noise ratio.
So if my noise power should be greater than what is the effect of on the signal? SNR, it will be more or less. If my my noise power should be greater than signal power, then what is the SNR? It will be bad or good? Sri, you said that signal SNR equal to signal to noise power. If it will be improve, it will be great, then whatever that SNR, how much SNR will be changes? Anyone from that class?
1:2 ratio, sir.
Yeah. So if my noise power should be more than signal power, then what happen? Kalyani,
Yes, sir.
what happen in that case? If in my
Can you
signal,
repeat once again, sir?
if my signal noise power should be, my noise powers is more than signal power, then what happen on signal to noise ratio? And what is the happen on the signal? Should signal should be recovered? Can we detect that signal or not at the output side? Jagannath, Parul, Manju Kumari, Meenakshi, Jagannath Nayak, can you answer that? Vidya, Kalyani, if my noise power should be that greater than signal power, then my signal will be destroyed in that case. We cannot identify what are the power of the signal in that case, and it will be reduced in that case. We need in our communication our signal to noise ratio should be more. It will be only in this case when we have the less noise in our signal. If our noise will be more in the signal, we cannot detect at the output side of the signal. We cannot detect. It have more bit error ratio, bit error rate in that case. And whatever the actual signal we have sent, we cannot receive at the output side. We cannot identify whatever the signal we have sent. So those short distance link depend upon the minimum power required or to bit error rate at receiver sensitivity and depend on the bit rate. Whatever the bit rate of the signal we have sent on that depend. Or for long hair link means we have the link of like that 100 kilometer of link. So can we transmit the signal without loss to 100 kilometer? Anyone in the class? Yes.
No.
So what we need that? Because suppose the amplitude of the current of my signal, like this signal I signal is my 5 ampere. It will travel through the long distance. It will be reduced in that case after 20 kilometers. It again reduce. It will again reduce. It will again reduce. And at output side I receive only 100 nanoampere current. So what will happen in that case? What happened? Because whatever the signal amplitude and output side, it is very less. We cannot identify that whatever the signal we have sent, it will receive that signal only or it will be only noise. So what we need, we put between that amplifier. We need the amplifier which amplify that power of that signal current. After 20 kilometer we have to put one amplifier, and it amplifier have also some noise. It have some also reduce that detection, some will affect on the signal. So we have also, it will power push the power of our signal. So it depend upon the amplifier which add on the noise. some signal quality will be degraded in that case, because it amplifier will also add some noise in that case. Okay, and our signal to noise ratio is directly proportional to square of the quality factor, SNR. Anyone want any doubt in this case? Any doubt? How can I get a signal and SNR equal to Q square? Any doubt? So what happened?
Can you please repeat it?
Yes? Hello? Yes, Jagannath?
Sir,
Yes, Kalyani.
Can you please repeat?
Yes, I will repeat it.
Okay.
Yes, Kalyani. You want to say something? Kalyani?
no, sir, no.
So, Jagannath, we already said that our quality factor we have defined I0 minus, sorry, I1 minus I0 upon sigma 0 plus sigma 1. Okay, we can return it to I1 upon 2, that it will sigma t square as the average of that q1 and q0. So q square we have defined, we have to square every one here, I square upon 4 sigma t square. T sigma t is transmitted standard deviation, total transmitted. Okay, here. So what happen since SNR is related to the average power of signal, we have take average power of signal and average power of the noise. We can write that high state current in time of the average. So we can write I1 equal to, what is average of I1 equal to I1 by 2. Okay. So in place of the I1 we have to replace with that I average. I average square upon sigma t square, because 2 and 2 this will be divided by sigma t square. So our SNR should be equal to the responsivity square upon power in square upon sigma t square in that case. So there, if we suppose that our signal have the quality factor equal to 6 and SNR equal to 36. Okay, some of the important we have to calculate that we have to take care of that thermal noise in this case. So for receiver sensitivity, I already explained you that receiver sensitivity in that P average in case of the thermal noise equal to Q upon sigma t square upon that RD. So from this equation and this equation we calculate SNR equal to Q square. It's a given relation beta SNR equal to Q square. So what happened in the short distance link, that we have only transmitted from 10 km of our signal. We have the parameter only that what of the average power of the receiver. So we can estimate that minimum bit error rate equal to less than equal to 10 to the power minus 9 for short distance communication. It's depend upon that bit rate, how much the bit rate of that, like 2 kbps, 4 kbps, 6 kbps we have transmitted in case of the short distance link. But what happened in the long distance like 100 kilometer and 1000 kilometer link, whatever the signal we have sent, it have some current like that, I average current like that 5 ampere, 10 ampere, 50 ampere, it will reduce after some travel some distance. So we have to add the amplifier which will amplify that signal again to again after 10 kilometer or 20 kilometer. But amplifier have some noise, it will add in between some noise, and it have. So what happened that when the noise will be added from the, like that we have the 4 amplifier from that 100 kilometer, 20 kilometer, it add the 4 times of the noise on the signal. So what it will be degrade that quality of the signal SNR, because noise power will be decreased but our signal power will remain with a constant. In this case our SNR will be bad, and we have to minimize that performance of that SNR in that case. So we have to provide that solution how to can minimize that SNR. So we have to put again some optical component which can reduce that SNR from the transmitter to receiver in that case.
Yes, sir.
So explain the quantum limit of the photon detection. What are the quantum limit? Anyone can tell me the quantum limit? So quantum limit will tell that you the minimum power required to achieve a certain performance. Like that receiver sensitivity, we have defined at power average. So whatever
The
that
receiver, I
value,
think, it will be short noise.
hello, हाँ
So the
जितना
receiver is in the short noise limited condition.
yes, short noise. So we have to, in that case, quantum limit with sigma thermal noise, we have to assume that 0, and we have to, in the quantum limit of photon detection, we have to we have to take care of the short noise only. This, okay. So
The thermal level should be 0.
yes. So what I think, what I explained before that, I that in that previous 3 to 4 questions, the we have, if you have to estimate that bit error rate, we require sorry, we required some receiver power, minimum power required that. So that minimum power, whatever that we have to, from that minimum power requirement, we have to calculate the performance of that optical link. What is the quality factor of the optical link? Whatever the receiver power minimum, whatever the noise, we have to calculate everything through that. What are the amplifier noise? We can calculate through that only this minimum power, that quantum limit of photo detection. Detection means we have used on the receiver side. Photo means photo will be detect that signal through the photo detector. In the last lecture, that week 7, we have already explained about the photo detector, how it work, what are the principle that photo detector work. So you can go through that. If someone is missing that class, I already put that video on that YouTube also, that you can go through that video. So in this, we assume that our thermal noise should be equal to 0, no dark current, ID equal to 0 in that case. Our efficiency of that detector should be 100%, that photo detector. So we have no multiplicity of noise, we have not multiple of the noise, we have assumed that no multiplicity of the noise in that case. So whatever the probability that photon receive a detector, we have to given that n number of photon that receive, that probability of that n number of photon received, the photon detector is given by E minus np की power n upon n factorial. Okay, where np is that average photon number. This np is the average photon number, and this np is given by equal to ptb upon hv. So p is the average receive power corresponding to the high state. But if our signal is like that, so average power of that we have taken the calculation, and TB equal to 1 upon B, B is equal to bandwidth in that case. So 1 minute. So B equal to 1 upon TB. So it is TB is the symbol duration, means whatever the duration of the one symbol, this duration will be explained by the TB. Okay. So for that instant, if average number of the photon is computed, be the 3. So NP equal to, suppose we have to NP equal to 3, then the probability of the detection of the signal, that we have given that P1 equal to e की power minus 3 upon 3 upon 1 factorial for one signal, n equal to 1 photon, that probability we have given to that e की power minus 3 upon 3, like that. So how much the probability of error? Anyone in the read the communication, that probability of P10 and P1 transmission average power in digital communication? Anyone have an idea? How can we that error we have dependent probability of the signal 1 and signal 0? in mathematics, or anyone have read that? P0 and P1. Probability of that power of the P0 plus P1 0 1, and we have to define like that. One. Anyone remember this formula? In class, anyone have remember? In digital communication, we have to calculate that in a signal that probability of the transmission of the signal 0 and signal 1. What are the probability that signal will be not transmitted and one bit will be transmitted? We have to some formula there. So P E equal to,
Sir,
we
we
have
have
to
the P equal to P1 by P naught by
P1
1 plus
into P01 plus P0 into P 1 upon 0. Okay.
P1.
So what is that
Yes, sir.
meaning of that? What is the meaning of that? So P1 P1 means probability of the signal 1 transmitted. P0 1 by 1 means we have transmitted 1 but we have received 0. Okay. So what are the, if we transmitted 0 1 and we have received 0, what are the probability of that? We have nomenclature like that. Like that P0 is the probability of the signal 0 we transmitted, and what are the P1 by 0, that we have transmitted 0 but we have received 1 in that case. Through this we can calculate the probability error of the signal. Okay. So we can calculate uh, so that in case of that optical link, the probability error will be defined like 1 bata 2 e की power minus np. Okay. So suppose I have given one question to you. If you anyone want to solve that, suppose that we have the bit error rate equal to 10 to the power 9. Okay. If the receiver is operating in the short noise limited condition, then what is the bit error rate in this condition? And what is that average power? These questions I have example. So you have to calculate a bit error rate in that case, and you have to given that 10 to the power minus 9 is the bit error rate, and you have to given that probability of PE in that case. So you can take this bit error rate in the log bit error rate. You have to define that this will be NP will become like that, your minus log into 2. So NP will become equal to minus log 2 into bit error rate. So your bit error rate you to given that from that formula, and it will be you to calculate that noise power, short noise power, if the receiver in the short condition. And from noise power you can calculate that PT by that power you can calculate from this formula. So anyone can in the class explain why do we need the optical amplifier? Why we need? And what type of the optical amplifier? And what is the specification for optical fiber amplifier? Anyone can explain?
Sir, the optical amplifier reduces the power level so that the light can propagate through the fiber. Attenuation level. It reduces the attenuation.
See that this is the distance we have traveled, and
Yes, sir.
this is our the power, launch power. Okay, and this is the sensitivity of our receiver. Okay, what happen? The signal will be travel and this will be reduced like that. Okay, Now it will be not move like that, not move like that. So what happen? That power will be reduced. Whatever launch power and whatever receiver power, it need to be amplified. Okay, to receive that minimum bit error rate. So we have put one amplifier here, one amplifier here, and one amplifier here, and it will be moved like that, one like that. Moved again, it will be amplified. Go to the maximum average power, then again the minimum receive sensitivity again will go, and like that it will be come at maximum operating power range in that case. So we need that amplifier power. What are the specification of the optical amplifier? How to you design it? What optical amplifier we need? What type of the optical fiber we need and what requirement that? So you can choose that optical fiber. What is that specification? If you any buy the mobile from the market, you need a specification that I require a 6 GB RAM, 192 GB memory, 5G communication will be there, some Bluetooth power 3.3 GHz will be there. Processor should be like a high processor, should be low power, high battery. So how you decide that optical amplifier? What parameter that is depend? Anyone can? Anyone in the class? So we require a good optical fiber amplifier. If we want to choose the optical fiber, the optical fiber have a unsaturated gain. Means it will be not saturated. The gain should be high in that case of the optical fiber. It required the optical bandwidth, the maximum optical bandwidth should be less noise figure. Maximum output power should be should be less the coupling losses. It has the maximum pumping efficiency, so it will be pumping more, it will more amplify that reach to that launch power. It should be not depend upon the polarization of light, should have the less crosstalk. Okay, so these are the specification we have to require. So anyone know that type of the amplifier? What are the type of the amplifier? Anyone use in that your company or that?
Sir, one is electronic amplifier and one of optical amplifier.
What is one is
Electronic amplification and one is optical amplifier.
so in optical amplifier we have used one iridium doped fiber amplifier that optical pumping use be done. One is the semiconductor optical amplifier which is made of the silicon, germanium, gallium arsenide, that semiconductor material, that is electrical pumping. One is the Raman amplifier that depend upon that wavelength of the light, that Raman physics, Raman phenomena. So in iridium doped fiber amplifier we have doped that optical, like that we have the optical fiber, and we have doped this optical fiber with that plus 3 ions. We have to do external doping in the fiber amplifier, and we use to that amplify that signal. In case of the semiconductor optical fiber, we use that electrical signal. We have to do the biasing of that signal, and this will amplify that signal. External biasing we use that electrical. In the Raman amplifier, whatever the signal will become through that wavelength of the light of that, like that lambda equal to 365 nanometer, 4 nanometer, we amplify that signal. That Raman light will be focused on some material, that amplifier material, and it will generate that current, and the signal will be generated that falls on that signal, and whatever light will fall, it will produce some electrons, holes, and it will amplify again that signal. So these are the three different phenomena you have to read through that lectures, and that depend on that. So this is the input power we have to given P lambda, and P out we have to through the gain we have to given that. This is the type of the optical fiber. I have already that iridium doped fiber here. This is the fiber, and in this we have to dope that iridium for that. And there is the coupler and isolator. This is the pump laser, and this is the pump laser to coupler, and this will isolate that signal. It will isolator will use to not to come back the signal. It will transmit only one direction, either forward direction or whatever reverse direction. So iridium doped amplifier, which is optically a pump laser, and that input light is coupled to silica fiber dope with the ER plus 3. I already tell you, using the wavelength division multiplexer, and the length of the fiber is typically 10 to 10 nanometer. So the fiber length should be like that, between that only. So one questions I have take that find the expression for that from the assignment. If you have any doubt from the assignment, you can ask me. Anything from assignment? This is for your homework. If you solve these questions, then good, or otherwise I will solve in the next class. So please note down this question. I will ask in the next class.
Sir, question number 13.
Question number
13 from the assignment.
13. A 1.3 micrometer digital receiver is operating at 100 Mbps at effective noise bandwidth like that. This question, thermal noise limited system. Jagannath,
Yes,
this
sir.
will be questions.
Yes, sir. The question is 1.3 micrometer digital receiver is operating. Yes.
1.3 micrometer.
Yes, sir.
Okay, okay. One minute. Give me 1 minute. So it bandwidth should be you have to given that 100 Mbps per second at bit rate you have to given, and effective noise bandwidth 60 hertz megahertz. The PN photodiode is negligible dark current. ID equal to 0, and quantum efficiency should be equal to 90%. You have to given. The load resistant RL equal to 100 ohm. Amplified noise figure is 3 dB. Amplified noise P amplified noise equal to 3 dB in the final receiver sensitivity for bit error rate of 10 to the power minus 9 to 10 to the power that. That formula that I previously you explained, that power in that P equal to 1 beta 2 into e to the power minus n P and that.
Yes, sir.
So you already that quality factor you know that 10 to the power minus that 12 and 10 to the power minus 9 is 7 and 6. From that you can calculate a quality
Yes,
factor. Okay, and you have to give
Yes,
that power of that receiver. You have to give the receiver sensitivity. That P average equal to that 1 by 2 Q sigma T square beta 2. You have to Q beta that RD. So you have to calculate that RD of that receiver. I think that this expansion will you give these questions answer.
okay, sir.
If you calculate this expansion, you have to give
Yes,
the
sir.
RD receiver list and that everything you have to given. Uh, one thing that
Yes, sir.
So quantum efficiency is given, so RD you can find out.
yes,
Then assume room temperature. Everything else is given for this thermal noise variance you can find out. Then Q square is given. That will come as in Q square. Q is given, so SNR you can find out.
U is given.
And that
Not Q
SNR.
so RD you can calculate to L lambda beta efficiency to that sigma T thermal noise. You have to given that previous class that 4 kT delta Fn upon RL, that thermal noise from previous week. That you have to take that also that. Okay, that thermal noise and that short noise formula from that previous class. And then you have to given that signal to noise ratio.
Yes.
I have already explained that Q square from that formula that I explained that RD square P average beta sigma T square. So that you get that receiver sensitivity P average you can calculate. Okay. So sigma T value you have to take that previous class. You have to take that. This will be related that week 7 and week 8 question that.
Okay,
O-
sir. I
Okay.
will go through this.
So you have
week 7,
to
right?
just remember that how much.
Sir, where is the link?
Yeah.
Sir, week 7 access link.
Week 7.
Last week.
Yes, sir.
Last week.
I mean,
You have to that how
so
thermal noise will be calculated. Week 7. I already explained that formula there. Week 7. That sigma t
Sir,
thermal
where
noise,
is the
that
link?
thermal noise variance will given equal to 4 kt
Okay, T.
delta f fn upon rl. So k is the Boltzmann's constant, t is that temperature, room temperature, delta f that bandwidth you have to given. This is noise figure for figure of noise, and that rl have to given you that in questions. And then you have to quality factor,
Okay,
you
sir.
have to given equal to SNR, and this will equal to your responsivity. You can calculate from that efficiency RD square P square average upon that sigma T square. Sigma T square already you calculate, RD you have to calculate, and quality factor you know that for that 10 to the power minus 9 and 10 to the power 6 you can calculate P average directly for both the case, for 10 to the
Yes,
power
sir.
minus 12 and 10 to the power minus 9.
Okay, sir.
Okay.
Yes, sir.
Anyone have any doubt? Should I stop? If you anyone any doubt, you can ask now, or you can post on that ask two questions on Google Classroom. Any question on chat box, Donik?
Check. Yeah, nothing.
Okay, Jonek, anything else you want to add something?
No, no. Next week there will be some MATLAB demo course or something. That's all.
So please be present on the class.
I
If
had
you are,
already sent a question to you the last week. You have ever not seen it, sir. Can this see it?
Jagannath, your voice you're not audible properly. Can you speak again? Can you pattern?
Yes, sir. Sir, I have shared a question to Jonak, sir, the last week. That's why I asked, sir. I think sir never seen it.
He will be reply maybe that no problem. Maybe he will be busy and maybe that. Jonek will be take on next class, or you reply on that ask two question on that.
It's receiver sensitivity questions. Where did you
Sir,
post?
yes, sir.
Okay, okay.
Okay, thank you. Please, if you have any friend
I have
that
made. Yes, sir.
yes, if you have any friend that have joined that same course, please motivate him to join that class, that live sessions. We have very less attendance. If you have any contact to 293 student, please them motivate them to join that. Okay, Jonek, anything else?
Yes, sir. Yes, sir.
No, no. I'll reply to this.
Yeah.
Yeah, we can close.
Okay. Thank you, everyone. Thank you so much.